In this video, we're going to discuss directing effects in disubstituted benzenes, so benzenes that have more than one substitution on them. The first thing that we need to know is that the more powerful activating group generally determines the outcome. So sometimes, like in the example below, you actually have two activating groups, and so the more powerful one is going to end up doing the deciding. If you have an activating group and a deactivating group, the activating group is going to win. So we're going to analyze this structure and then figure out which products are possible. So both substituents are ortho-para-directing and activating. The amide is actually stronger because it has a lone pair which is able to contribute to resonance forms, whereas the methyl group is going to be able to stabilize a carbocation due to electron donation. The lone pair on the amide can actually contribute. So that is going to be our stronger activating group, and it gets to win. So if we think about our possibilities here, these groups are para to each other. So a para substitution is not going to be possible. So what we have to decide is whether the ortho position to the amide is better or the position that is ortho to the methyl group. Since the amide is the stronger director, we are going to put it in the ortho position to the amide. Because these are both activating, we're probably going to see a little bit of each product, but this one will be major and this one will be minor. In this example, we have two different groups that are meta to each other, and we are going through a bromination reaction. I've already labeled all of the positions in which our next substitution can occur, but let's go ahead and look at this in the exact same way that we did on the previous page. So first, which director will dictate the outcome? We have a carbonyl group, which is a meta director, and we have a hydroxyl group, which is an ortho-para director. Remember that ortho-para directors are going to win over meta directors, which means our hydroxyl group is the winner. So this lets us eliminate a position already. If the carbonyl were in charge, the product would end up substituting in the B position. Since the carbonyl is not going to win, we're not going to substitute in the B position. B is also meta to the hydroxyl group, and the possibility that you would put a substitution meta to an ortho-para director is very, very slim. So our next question is, will the bromine be ortho or para to the hydroxyl group? And if ortho, which ortho position? This one helps us out with one really easy situation, and that is position D. D is ortho to the hydroxyl group and to the ketone. It is directly in between two substituents that are meta to each other. That position is going to be so sterically hindered. You almost never put something in between two meta substituents. So we're going to go ahead and cross that one out. That means that we are going to have the possibility of substituting in position A and position C. Now, what you might recall from previous slides is that the ortho position tends to be more electron rich, especially when you have a substituent that has lone pairs that can contribute to the resonance forms. So substituting in position A is really likely. We also have position C, which is ortho to the carbonyl. The carbonyl is larger, so position C is probably a little more sterically hindered. So those are our different things that we have to consider here. Overall, position A is definitely the better position. So these are our two possible outcomes, and the product that has the bromine ortho to the hydroxyl group is going to be major. And the product with the bromine para to the hydroxyl group and ortho to the carbonyl is going to be minor. And if you further advance the slides, you'll see the logic being put out again. So this brings us to a synthesis problem. Go ahead and pause the slides and think about it for a second. Remember that you have to consider what the directing effects are of each of these, and consider how the order of adding in these substituents has an effect on the outcome. This is a really great example of a very simple electrophilic aromatic substitution synthesis. The only thing that you have to think about is the effect of the order of your reagents. So if we were to add on the bromine first, we would have an ortho-para director. So then going through a nitration reaction from here would give you only the ortho and para products. And our goal is the meta product. So this is not going to work. We're going to have to do this in the opposite direction. So what we want to do is add in nitric acid and sulfuric acid first, so that we end up with nitrobenzene, and then follow it up with the conditions for bromination, so that we end up with bromine in the position that is meta to the nitro group. Very simple.